what do you need to do to make these product forms from there? So that is a question that now you need to figure out what types of reactant, reactant you need to create. So first of all, the carbonyls are here. So you can imagine that this carbon is that carbon. So we need to introduce the propyl groups on the less substituted side. So you gotta make the enolate on the less substituted side. So what condition do you need to use? Well, that's a kinetic enolate you gotta produce. So producing a kinetic enolate, you gotta using strong base like an LDA, low temperature. That makes a kinetic enolate. And that affects the propyl bromide, right? We need the propyl groups there. So propyl bromide, it makes an attack there by SN2 reaction and kick the bromides out. You can make this. But the key for solving this question is you gotta recognize that you need to make a kinetic enolate. If the propyl groups are sitting on that side, more substituted side, then you gotta produce the thermodynamic enolate. Then you need to use a weak base like dioxide, ethoxide at the room temperatures. But on the other hand, this is basically what I was just talking about. If you're using like a methoxide, which is a weak base, it's a thermodynamic conditions. So these more substituted proton will be pulled out because each time you only make a fractions of enolate. So it's an equilibrium condition. So more stable enolate gets produced, and this is the one that goes for the reactions. First of all, it's stabilized by the molecular structures. And then if that go for the same propyl bromide, then you're gonna get the propyl group sitting on the more substituted side. So if you choose a wrong base, you cannot carry out the synthesis the same, and expecting this product. It's gotta be kinetic enolate. That's what you need to recognize. There's another way to do this is actually going through the enamine. If you mix an enamine, then alkylation is going to be done on the less substituted side. So if it goes to room temperatures, you get the less substituted condition alkylation. So this is something that I want you to be familiar with for preparing the quiz and test. And these reactions are pretty simple again. That is basically this. And then you gotta attach this acyl chain. And if you remember that, it can be done through like enolate, or it can be done through the enamine as well. Let's say you using whatever the base, because there's only alpha hydrogen it can be pulled up. Strong base, weak base doesn't really matter. There's only one hydrogen there. So there's no reason for going for the kinetic or thermodynamic in this case, because there's only one side you can make an enolate. Kinetic thermodynamic enolate matters when there's two different hydrogens are available. This is just one hydrogen. So whatever the base you use, you'll get that enolate. Then you need the acyl chain need to be added. So that's going to be something like a methyl ester. So these carbonyl have an ester there. So what happened was this enolate makes an attack, and then you're going to get tetrahedral intermediates, but it's going to come back and remake the carbonyl by kicking the methanol out. Then you can have an acyl groups attached to that carbon. And enamine is another good way to do this. Enamine with these ketones, we're going to get the, secondary amine and ketone will make an enamine. That will be the same reactant. It's going to make an attack. It's going to go for the tetrahedral intermediate. It's going to come back, make the carbonyl by kicking the methoxy groups out. So you're going to get products formed with the acid iminium ion, which gets hydrolyzed by the water, so it becomes a ketone. So either way is perfectly fine.